I want to bring out our next speaker, Mr. Vik Malyala from Supermicro. Come on out, Vik. Yes, my man.
Thanks. They said I can't get on the stage without these glasses. Okay, we'll see. Just before getting on the stage, I was talking to Ted, and he said, Vik, you're talking about 200 kilowatts per rack, but already there are talks about much larger than that, right? I mean, for sure, we all know. Jensen has announced a couple of months ago about 600 kilowatts per rack, and earlier this week, Google announced about 1 megawatt per rack. So I said, well, actually, I have changed some of this because it's not about just 200 kilowatts per rack, but it's more to do with what is happening, what are we seeing, and what we could be doing. I think that's basically what I am hoping to say and do this here. So I'm Vik Malyala. So I'm planning to talk about the data center innovation and challenges, because this is primarily what we are pretty much dealing with on a day-to-day basis. So I kind of see Supermicro is very much synonymous with AI. In other words, the growth that we are seeing in terms of adoption of AI and the infrastructure needs that are just booming, we are kind of capitalizing on it. We are being ready, bringing the right platforms and solutions. I'm not going to talk much about all these things, but basically the idea again here is, as we look at Supermicro, we are kind of being a very important piece of the puzzle in the infrastructure space. And for what it's worth, because of that, we're kind of bridging the gap in terms of getting adopted widely. So we are number one in terms of IDC as of a month and a half ago, right? Which is quite interesting for Supermicro, because we started with very humble beginnings, and we have still a long way to go. I'm not trying to brag that one, but here is where we are. So manufacturing point of view, San Jose, Silicon Valley, this is where the company is established, and 70% of our manufacturing happens here in San Jose, and the rest of it happens in Taiwan for the Asia-Pacific operations, and also we have manufacturing operations in Europe that happens in Netherlands. So this is basically the kind of general idea of what Supermicro is. This slide, I was trying to understand what I plan to say, right? So when I take a look at the models, the parameters is an absolute important thing, because that kind of determines the size of the model. When I take a look at it, almost every year, that's kind of doubling. Maybe 8 months or so, the number of parameters that is being driven, that kind of addresses the size of the model. That's doubling. And then the amount of data and the data sets, from what I read, I just Googled it, by the way. So it's the data is basically doubling every 8 months, and the data sets are tripling every 12 months. This basically requires a humongous amount of compute power. What they are saying is about in every 6 months, the amount of compute that is needed in running the AI infrastructure, that is needed, right? So it's a combination of all these things. It's not just a cookie cut method, a combination of it. While all these things are expanding, the thing is that there is a compute that's coming from CPU and GPU. These are also increasing quite a bit. Every couple of years, it's 2.5 times the performance improvement you are seeing. So at one end, the requirements are kind of going leaps and bounds. At the other end, the compute power and the ability to handle this kind of workloads is also evolving. But the problem is, this is coming at the expense of having more and more and more power-hungry devices. So what used to be a 300 to 400 watts per GPU, now we are talking about already at 1400, 1500 watts. And it's going to go close to 2000 or beyond. This is where the trend is, typically in a HGX type of environment. If you talk about super chips, now we are talking about a GPU and also a CPU on a single chip. It goes even beyond that. So this creates a different type of problem in terms of how we are actually fitting that into the systems. The second is, the type of models, as they are getting bigger and bigger, as of now, we are talking about maybe a 5 trillion parameters maybe in the next year. But irrespective of how much improvement that's going to happen in this, it's going to continue to grow, and probably maybe a 10, even 100 trillion parameters, maybe 4 or 5 years down the road. I don't know, just a guess, right? But when you start looking at that, how are these models are going to fit in a traditional infrastructure? Because these things need to be made into smaller chunks and going to be distributed across multiple systems and whatnot. So it's an important thing for us to pull all these things together and pack it in a smallest form factor if at all possible, because systems need to be connected using a very high speed, low latency fabric that need to kind of bring all these nodes together and be able to speed things up. So it's not just about a system sitting by itself in any form factor. There is a need for us to increase the density and reduce the latency, improve the bandwidth between these nodes, as well as bring the storage close to that in order to get the GPUs busy with whatever they are doing. So that's kind of an equation that we are trying to figure out. And from the data center point of view, this poses an incredible challenge. I think as someone was mentioning, 98% of the data centers are outdated. I mean, to some extent it's true, because in the industry being long enough, we know that never really changed. 10, 20 megawatt type of data centers, if someone has, they are golden. But if someone basically comes and talks to Supermicro today and say, oh, I am having this huge data center plan, having 10 megawatts, okay, then what? Because we're talking about gigawatts of power that is being built into these data centers in a brand new data centers, right? So you have these traditional data centers that is going to be retrofitted to use the infrastructure. And then you also have new data centers that are going to build from scratch that is going to accommodate the infrastructure. So a bunch of things, I'm not going to read everything, but the idea is in order to handle these large language models and training clusters that are only getting bigger and better, we need to figure out a way to handle that more effectively. So this is something that all of us have seen probably. This is something from NVIDIA. We can kind of see how quickly the size of models is increasing. Today we are talking about 1.7 whatever trillion parameters, but it's just not enough. Very soon it's going to be much, much bigger. So we need to be prepared for that. What does it mean in terms of the hardware? So when I take a look at it, CPUs already are at 500 watts. It may go slightly higher, but processing is something. Most of the time, CPUs are basically using a pre-processing of the data, and they have a bunch of memory that is actually going to pass through that to keep the GPUs busy. That's pretty much what's happening in much of the AI infrastructure. But then if you're talking about data processing prior to get the GPUs using that, there is a whole bunch of compute power is needed with high-frequency CPUs, queues, and whatnot. That's going to improve that part. And then the next aspect of it is keeping the GPUs busy, which basically means the connection between the CPU and GPU. Bunch of PCIe lanes at this point. PCIe Gen 5, it's going to probably be Gen 6 and others in future. As for the GPUs are concerned, the power is already moving towards 1 kilowatt or more, and the super chips in a similar area. So in a system level, when you take a look at it, there is only so much of air that we can move from this one. That actually kind of the limiting factor in this. And so air-cooled is actually great for majority of the data centers, mainly because it just works. However, there are limitations with respect to what it can do. That's where the liquid cooling comes into picture. So what we have seen is that as things go past 20 or 25 kilowatts per system, pretty much you end up going to liquid cooling. That's what we are seeing. And today, as we speak now, majority of these rack level solutions that we are deploying, they're going anywhere from 100 kilowatts to 200 kilowatts. So when I talked about 200 kilowatt racks are here, it was unheard of not too long ago, but it's already getting outdated. Even before the 200 kilowatts, we are saying, it's a great thing. And the way things are happening in the very near future, it's going to be insufficient. So data centers takes years and years of time to build. So how are they going to prepare? That's one of the reasons I think Jensen has actually announced, saying 600 kilowatt racks are coming. You data center guys go figure it out in the next couple of years. So modernization of the data centers is needed. One of the things is that air and liquid, we look at it in terms of the need, but at the same time, as things are getting deployed at giga scale, we're talking about 500 megawatts and a gigawatt and things like that, traditional data centers kind of burning almost 50% of the energy on cooling alone. That's significant. So that actually can be recovered if you were to use liquid cooling. So if you take a look at a good chunk of Supermicro's customers today are actually either retrofitting the data center or building the brand new one to take liquid cooling as a part of it. The largest clusters that we have deployed are actually liquid cooled. But still in the overall scheme of things, I would say 15 to 20% of them are ready. But In the next year or so, I see a lot more of them, thanks to GB200 systems that NVIDIA announced, which pretty much requires liquid cooling. And the data centers, believe it or not, they need to figure out now how to make this more flexible, right? So even if you have a gigawatt or whatever, it almost coming to a point, if you have a megawatt of rack, 5-6 racks is basically going to take all the space away. I mean, in a small data center, rest of it you can probably play ping pong or snooker or whatever, right? That's pretty much where it is. And so it's about the power distribution that need to happen, the ability to kind of flexibly manage it, and you need to be able to handle different form factors, and you need to be able to, let's say, manage it in a more effective way, right? But the other aspect of it is, already we are talking about 2 to 3% of the power that is being generated is going for data centers. So how do we reduce the carbon footprint? So sustainability and other things are also coming. So every data center, as we start looking at, they need to start paying attention to this more and more and more. So just kind of looking at okay, it's environmental friendly and all is only part of the story, right? So I just took an example. In this case is an MI300X. The same equation actually applies to if you're using H100 or B200 or whatever. So if you were to use a system using air-cooled, and if you are using with liquid-cooled, assume that around 75 to 85% of the heat rejected using liquid, which translates to around 25 to 30% in terms of the net savings, so which is quite significant. But once you add it at a data center level, if you're eliminating some of the UPS and few other things, the savings is going to be quite significant. AI infrastructure is obviously the most important thing, but at the same time, it all goes with the compute and storage that go along with it. So what we have done is to make sure that if someone is building a data center with liquid cooling support, whether you are using a compute, either Intel-based or AMD-based, whether you are using GPU platforms, again, NVIDIA-based or AMD-based, for example, and any kind of fabric that you are using, we are figuring out a way to get liquid cooling into that. That way, the overall data center management becomes somewhat easier. So what does it mean today? Today, if you take a look at it, the ones that are kind of getting adopted quite easily and a lot is the B200 platforms from NVIDIA, the HGX B200. So 2 of the common form factors, 8 of the systems in a rack is a 4U form factor, and the other one is 12 systems per rack, which basically gets 96 GPUs in a given rack. But at the same time, the minute you go to GB200, this is the first generation of the NVIDIA platforms, right? So you're talking about 130 kilowatts. 2 years down the road, the same thing is going to talk about 600 kilowatts, right? But today, the data centers, in order for them to be relevant, they at least need to support this. Whereas if you are using on the AMD side of it today, the MI325X, again, depending on whether you are using 8 systems or 12 systems per rack, you are going to 150, 160 kilowatts. But then the very soon to be made available, which is the MI350 series, we're talking about 170, 180 kilowatts per rack. So when I talked about 200 kilowatt racks is needed, that is right now. But if you talk about just the same topic, if you have to ask me next year, 500 to 600 kilowatts is not unreasonable to look at it. So this is the problem. Now, how are the customers going to take advantage of it? Because it's too many variables, right? So what we are basically trying to do is to minimize the barrier to adopt it. So effectively what we are trying to do is the cold plates that are required to take the heat out from the silicon. And basically in a typical system, the CPU, the GPU, the memory, all these devices, and the PLX switches, if at all, and any kind of VRMs, all these things are liquid cooled using the loop. That basically rejects majority of the heat. Then the systems basically need to take that and put it in a rack. In a rack, you have a cooling distribution unit and the cooling, all the plumbing that is required for the CDMs. And externally, you need to figure out a way to move the heat out from the system, which is basically the chillers. So we are kind of bringing end-to-end game. Not necessarily everything need to be from Supermicro, but at least if someone wants to adopt it, we are going to make it easy for them to do that. So that's where the direction is. But then when you start looking at all this infrastructure, people are so used to managing the systems by themselves, right? I mean, there are so many tools available. But when you start taking a look at the data center, especially when you have CDUs, CDMs, now you have the systems and you have cold plates with sensors and you have the chillers external to the data center, all these things need to have a way to be managed. So if anything happens, one can actually quickly react and do that. So this is another thing where we have something called SuperCloud Composer that facilitates that. Okay, with all this, what are we trying to do, right? So this is one of the things that's public, so I'm only going to share this. So this is at XAI that we have deployed, where it's the first 50,000 GPU deployment that we have done, which a lot of people talk about getting done in like 122 days. This is done with liquid cooling, and is the first of its kind in it, at that time. And the second phase of the same amount also went in, right? Why I'm saying that is that this basically started from scratch in a typical warehouse type of setting. From there to completely liquid cooled systems that we were able to do. And this only possible because we work with the customers and then we work with our suppliers to make it happen. The reason I'm again mentioning this is because as things get complicated, it takes a village. So we're all in this together, and we need to understand what are the things that are coming up. In the rest of the sessions, I'm assuming that we will know more about other technologies that are being brought in. So one is the software piece, but on the infrastructure side, we need to be prepared for that so we can work closely with the data centers, set the expectations for them to build the right type of data centers so we can make it happen. That's all I wanted to say. Thank you.